Okay, let's talk once again about types of reactions. I talked about that a little bit at the end of the last video, and they come in two principal types in this section. We'll talk about metathesis reactions, which are reactions of exchange. That's just where you have ionic compounds principally, or that have cations and anions, and you react it with another one and they swap partners. Okay, so they come in two forms: precipitation reactions and neutralization reactions. We've already talked about neutralization reactions in the form of acid-base reactions. Okay, and that's where we make water and a salt, and I'll talk a little bit more about that. So metathesis reactions, sometimes these are called double replacement. See if I can spell replacement. Okay, you know, the cool thing about having such terrible handwriting, sometimes people can't tell whether you misspell words or not. And that, you know, that's keeps you safe. All right, but precipitation and neutralization reactions are the two type of metathesis reactions we're going to talk about. And then we have reduction oxidation reactions. And when we talk about reduction oxidation reactions, sometimes those are called single replacement reactions, but oxidation is something you know of as corrosion. So when a metal corrodes, we call that oxidation. Also, the batteries that you have in every device that requires electricity that you walk around with, combustion reactions are also in the category of reduction oxidation reactions. Let's deal with precipitation first. So here we have compound AX and compound BY, and they go to the party. And so this pair and this pair are going to change partners. So here's what's going to happen. A comes to the party with X but leaves with Y. And B comes to the party with Y but leaves with X. I think I used that little analogy last time. So these two compounds swap partners. So that's why we might call this a double replacement reaction. So double replacement. Both partners have swapped. All right, so here is a real precipitation reaction. And in this particular case, we're just making a comparison. A is silver plus one ion. X is the nitrate anion, so there's your X. And then B is potassium ion over here, and then Y is your iodide ion. These are all ionic compounds, each and every one. But A is going to get together with I and form a precipitate. This is actually a solid, guys. It's a precipitate. And you can always tell precipitates because they fall right out of solution. All right, at any rate, so they've swapped partners. This is a double replacement. Okay, since this compound falls out of solution and is the precipitate, what we call this is the driving force for this reaction. And what driving forces do is they remove free ions from solution, and we'll dig into that a little bit more. And a precipitate is one of your four driving forces that you can have for these metathesis reaction. It's just the formation of a solid. So let me show you how that works. First of all, driving forces, it's a product of a reaction which removes ions from solution. You remember ions, these are charged particles. They either have a positive charge or they have a negative charge of some kind. And on the product side of a reaction, the driving force will remove those free ions from solution. And it's only on the product side. So don't look for the driving force for a reaction on the reactant side. It only occurs on the product side. So we've got 4 different types. We've got formation of a solid, a precipitate. We've been talking about that. Oh, that's how you spell that. Great. Formation of a gas. You can always tell when a gas is forming in your chemical reaction because your reaction bubbles. When the bubbling stops, that's when the reaction is over. Formation of a weak electrolyte. Usually the weak electrolyte that you're going to see form is a weak acid. Okay? And this is an acid that is not one of your 7 strong acids. So if you see a weak acid over on the product side of your metathesis reaction, dollars to donuts, that is the driving force for your reaction. Okay? Formation of a non-electrolyte. And the non-electrolyte that we see forming in neutralization reactions is water. It is, on the product side of your reaction, very often going to be a driving force for your reaction. So let me show you what I mean by all of that. So here's a precipitation reaction. So what I have here is I have potassium iodide. Now when I put potassium iodide into water, what it does is it dissociates into the iodide ion and the potassium ion. So each one of these little dudes is indicating a potassium ion, and these big old guys, these are the iodide ions. So they are free ions in this solution. And in the other beaker, before I mix these two together, I have lead to nitrate. And so that's what lead to nitrate looks like as a compound, as an ionic compound. Now what we're going to do is we're going to take the lead to nitrate, we're going to put it into solution. And what it does is it dissolves or dissociates. The same thing's true for the potassium iodide. And that means it comes apart. So here are the lead 2+ ions. Here are the nitrate ions. They are completely dissociated. Notice it's a 2 for 1, so you have twice as many nitrate ions in that dissociation as you do lead 2 ions. Now, here's what we do. We mix them together, and as soon as we mix them together, we form a solid. And that solid is the lead 2 iodide. So here's what happens. You get lead, it's got a +2 charge, and so you need 2 of these -1 iodides to go with it. And this is a solid. It's a precipitate, and it's indicated right here. You see it fall to the bottom, and it's yellow, just so you relate the photographs to what you're seeing on the particular view. But what you have still floating around here are potassium ions and the nitrate ions. The nitrate ions and the potassium +1 ions, they are still free ions. They haven't been removed from solution. In effect, what they're doing, and I'm just going to go ahead and put that up here, they're still in aqueous solution. They're still dissociated. They're sort of watching the reaction happen. They're watching what's going on down here, and so we call them, these guys right here, spectator ions, because all they do is they watch the actual chemistry that's going on. And that's an explanation of what we're going to see. All right, so let me show you the video. Okay, here is your lead 2 nitrate. Here's your potassium iodide. And what we're going to do is we're going to mix them. And as soon as you see the lead 2 nitrate interact with the potassium iodide, the lead immediately grabs hold of the iodide, forms this yellow solid, which gravity will cause to drop out of solution. It'll head to the bottom. That's what we call a precipitate. This is precipitation. All right, let's talk about strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes can never be driving forces for a reaction. Weak electrolytes, these can be driving forces. Non-electrolytes can be driving forces. So water, this is a non-electrolyte. So non-electrolytes, those can be driving forces. So if you see water on the product side of a reaction, it can be a DF. That's driving force for a reaction, not necessarily a precipitation reaction. That would be a neutralization reaction, most likely. This is a molecular compound. It is soluble, but there's no ionization. It's a non-electrolyte, so technically this could be a driving force as well. But this is sodium chloride. It dissociates completely in solution. So in any aqueous solution, you will never see a sodium cation associated with a solid. Okay, so these will always, or sodium cation will always be a spectator ion. Strong electrolytes can never be driving forces. So if you see a strong electrolyte on the product side of your reaction, do not choose that as your driving force because it can't be one. What driving forces do is they remove ions from solution. And strong electrolytes, they're putting ions in solution. Let's see what else we've got. We've got HCl. It's a strong acid. It ionizes completely, so it's a strong electrolyte. It can never be a driving force for a reaction. Now, that doesn't mean that chloride ion can't be associated with a driving force, or that hydrogen ion can't be associated with a driving force. But if it's HCl, it can never be a driving force because it is a strong electrolyte. Now this is a weak acid. This is acetic acid. It's a weak acid. If you see a reaction where acetic acid is over here on the product side of a reaction, if it's a weak acid, it's a weak electrolyte, and this can be, and probably is, a driving force for the reaction that you have, and I'll show you an example of driving forces. So you're going to have to become very familiar with non-electrolytes, strong electrolytes, weak electrolytes, and precipitates. Let's deal with precipitates first. So in order to recognize precipitates, you need to know your solubility rules or solubility guidelines for ionic compound. Here we go. All right, so what do we mean by soluble ionic compounds? So if I have an ionic compound like sodium chloride and it dissociates completely, what we mean is that is a soluble ionic compound. That is, dissociation occurs. And the way that we predict whether a particular compound is going to dissociate or not is we look at the anions. That is where we begin to take a look at that. Now, if an ionic compound has, let's say, nitrate or acetate, these are always soluble. What do we mean by that? We mean that they always will dissociate completely into their ions. There are no exceptions. That's why I have none over here on the important exceptions. There are no exceptions to nitrate and acetate being soluble ionic compounds. All right? So if I see, let's say, lead to nitrate, that is a soluble ionic compound. It's going to dissociate into lead 2+. We'll put aqueous out here, and we'll put the two nitrates out here. You actually saw this one in the video. All right, and so this is going to be a soluble ionic compound because it's a nitrate. And I don't care what other metal you put with nitrate, it's going to dissociate into its component ions. Okay? They're always going to be strong electrolytes. And the same thing's true for acetate. I could replace nitrate with acetate in both of these cases. Always soluble, always strong electrolytes. Okay? All right, no exceptions. Let's take a look at chlorides, bromides, and iodides. Now, they're mostly soluble. So you could see here, sodium chloride is soluble. I could have, let's say, iron 3 chloride. That's going to be a soluble, strong electrolyte. And how did I tell that? Well, because this chart, this set of guidelines here says that chloride is always associated with a strong electrolyte, but there are exceptions, and here they are. And you're going to find these are exceptions most of the time. Silver, mercury, and lead compound. So what does this mean? This means that if I have silver chloride, that's a solid. If I have mercury chloride, that's a solid. That could be a precipitate. And lead 2 chloride, that's a solid. That can be a precipitate. But if I take any other metal and I put it with chloride, any other metal than silver, mercury, or lead, that's going to be a strong electrolyte, like iron 3 chloride. These are dissociated ions. That's a strong electrolyte. Strong electrolytes can never be driving forces. So chloride ion, bromide ion, iodide ion will mostly be soluble unless I put them with silver, mercury, or lead, and that's for any one of those. Here's sulfate. If sulfate is combined with any other metal than strontium, barium, mercury, and lead, it's going to be soluble. It'll be associated with strong electrolytes. So all these anions that are on the top half of the solubility guidelines, these are mostly soluble anions. These are the exceptions to that solubility. So strontium sulfate. So strontium sulfate would look like this. That's going to be a solid. That could be a driving force. Barium sulfate looks like this. That can be a solid. That can be a driving force. Mercury sulfate. That can be a driving force. And lead sulfate. That can be a driving force. So these are the exceptions over here. All right, you take sulfate, you stick it with any one of those on the product side, you got a driving force. But you put sulfate with any other metal, any other substance, and it's a strong electrolyte, and it cannot be a driving force. That's the way to read this table. Let's take a look at insoluble ionic compounds. These are ionic compounds, and we're looking again at the anions. These are mostly the insoluble anions. Anions that you put with metals, they tend not to be soluble. That's different from the top half, where these are anions that you put with most metals and they tend to be soluble. These tend not to be soluble. But there are exceptions, all right? So the exceptions over here are the strong electrolytes. The exceptions in the top half are the driving forces, the precipitates. All right, so we're going to focus on the bottom half now. So these are mostly insoluble ionic compounds. So I can put pretty much anything with the sulfide ion, it'll be a solid, it'll be a precipitate if it's on the product side. However, if I put it with the ammonium ion, that looks like this. Okay, remember the ammonium ion has a +1 charge. So if I'm going to stick it with sulfide, I need 2 of them. Okay, that is going to be a strong electrolyte. That can't be a driving force. So it's exactly the opposite of the exceptions up in the top half. The alkali metals. So if I put, let's say, one of the alkali metals is potassium, so K2S, this is a strong electrolyte. Can't be a driving force. Let's use calcium. Here's calcium, and it's got a +2. Sulfide's got a -2. So that is going to be aqueous. It can never be a driving force. Same thing here, same thing here. Barium sulfide looks like this. This will be soluble. Okay, and it can never be a driving force. So up here, you take these, with the exception of nitrate and acetate, which are always soluble. You take these down here. Here's the exceptions. Okay, these will be precipitates. Down here, the exceptions will never be precipitates. All right, so you're just going the opposite directions. Carbonates, ammonium cation with carbonate, so that would look like NH4, got to put parentheses around it, carbonate. That's going to be a strong electrolyte. It can never be a driving force. But you put anything else with carbonate. Okay. Oh, and that's true for the alkali metals. We're going to learn that. Alkali metals are always soluble. Always soluble, which means they can never, ever be part of a driving force on the product side. All right? But carbonate. Okay, let's see this. Barium carbonate. That's a solid. That's a driving force. These are mostly insoluble compounds. Let's take a look at hydroxide. Hydroxide, if I take, let's say, iron 3 hydroxide, that's a solid. It's not a base. Doesn't want to be a base. It wants to be a solid. It's a rock. It's a stone. So that can definitely be a driving force on the product side. But notice that the alkali metal cations are always going to be soluble with hydroxide. Those will be your strong bases. Ammonium hydroxide is soluble. Calcium, strontium, and barium hydroxide. So barium hydroxide. This is one of your 8 strong bases. That can never be a driving force. All right? Remember that the solubility rules are for ionic compounds, not for molecular compounds. So this is only for ionic compounds. The top half, the anions are mostly soluble, with exceptions for everything except nitrate and acetate. Those guys are always soluble. On the bottom half, these are the insoluble anions. Here are the exceptions. These are the cations you can hook up with the anions on the bottom half. These will always be strong electrolytes, and they can never be driving forces because they are strong electrolytes. Okay, so you need to learn your solubility rules. I spent enough time on that. Hints to remember: all nitrates are soluble. Nitrates, these guys, you see a compound with nitrate in it, it's soluble. Same thing's true for acetates. You see an ionic compound that has C2H3O2 in it. And remember, this is always for ionic compounds, not for molecular compounds. These guys are always soluble. They can never be driving forces. All alkali metal salts are soluble. Alkali metals: lithium, sodium, potassium, rubidium, and cesium. You see any of those 5 alkali metals, it doesn't matter what the anion is. It could be, hydroxide, it could be sulfide, it could be carbonate or phosphate. These are always soluble. They're always associated with strong electrolytes. They can never be driving forces because they're always associated with never be driving forces because they're always strong electrolytes. All ammonium salts are soluble. Ammonium cation, NH4 plus, is the ammonium cation. So I don't care what the salt is. It could be NH4. Let's make this phosphate. Phosphate is one of those anions that is not particularly soluble, but if it's with the ammonium cation, it dissociates into 3 ammonium cations and 1 phosphate 3 minus anion. These are always, ammonium ion is always associated with strong electrolytes and can never be part of a driving force. Silver, mercury, and lead salts are generally not soluble. The only exceptions to that will be nitrates and acetates. All right, so if you see silver, let's make a couple up, silver bromide, that on the product side is a driving force. It's not soluble. If you see mercury chloride, that is a solid on the product side. That is a driving force for a metathesis reaction. And lead to iodide, that is a solid. That's the yellow one that you saw the video of. All right, halide salts, chlorides, bromides, iodide, generally soluble. The only exceptions are silver, mercury, and lead salts. So which of the following compounds is insoluble in water? Insoluble in water. All right. So you can stop the video and use your solubility rules and try and figure it out. But I'm going to go ahead and talk about it. This is an ionic compound. That's acetate. Now you know that silver, lead, and mercury compounds are generally not soluble. This is silver. However, this is acetate. There are no exceptions to the solubility of acetates and nitrates. So this guy will completely dissociate into silver ions, aqueous, okay, and acetate ions, aqueous. This is potassium sulfate. Sulfates are a little bit complicated. They're mostly soluble, but there are exceptions. But this is an alkali metal, potassium. So this is going to completely dissociate into potassium plus 1, aqueous, plus sulfate, aqueous. It's got a 2- charge. It can never be a driving force because it's an alkali metal salt. And all alkali metal salts are strong electrolytes. That means they're all soluble. They all dissociate. So never choose it as your driving force. Alkali metals will always be spectators. This is a nitrate. Yes, iron is not particularly soluble, but it's with nitrate. There are no exceptions to nitrates. So you're going to have iron 3 plus, aqueous, plus 3 nitrates, aqueous. Okay, that's a strong electrolyte because all nitrates are soluble. All right, this is zinc sulfide. And sulfides, this guy right here, if you look on the bottom half of your solubility guidelines, what you'll see is that sulfides are mostly insoluble in water. There are a few exceptions like ammonium cation, ammonium sulfide, any of the alkali metal sulfides, those will be soluble. Calcium, strontium, and barium sulfide will be soluble, but zinc is not one of those. So here's what it'll do. If it's on the product side, it's going to be your driving force because it is insoluble. Okay, so learn how to read and memorize your solubility guidelines. All right? All right. The formation of which one of the following compounds will act as the driving force for a metathesis reaction. You are looking for either a solid precipitate, a gas, a weak electrolyte, or a non-electrolyte. All right? And potassium hydroxide is one of your strong bases, so it completely dissociates into its ions, and so it's a strong electrolyte. It can never be a driving force, never a driving force, because it's a strong electrolyte. Sodium nitrate, this is a nitrate salt. It's sodium, it's an alkali metal salt, and both of these are always soluble. So this will always be a dissociated pair of ions in aqueous solutions. So that's going to give you this. And so never, ever, ever a driving force because it is a strong electrolyte. Remember, strong electrolytes can never be driving forces. This is a salt, magnesium chloride. Most of the chlorides are soluble, and the only exceptions are silver, lead, and mercury. Magnesium isn't one of those, so this will dissociate into aqueous solution and 2 chloride ions. It's a strong electrolyte, so never a driving force. So I've got 3 wrong answers here for driving forces. Remember, driving forces remove ions from solution in a metathesis reaction. But this is a weak acid. Now here's what fools people. You go, well, wait a minute. You said acetates are always soluble. Well, they are in what kind of compounds? Ionic compounds. This is a molecular compound. And molecular compounds, the solubility guidelines don't apply to those. So this partially ionizes into H plus and acetate. So it will put some ions in solution, in aqueous solution, but it's a weak electrolyte. And weak electrolytes will remove ions from solution. I will show you how this can be a driving force. It's a weak electrolyte, and weak electrolyte can be a driving force for a metathesis reaction. Okay. Whew.